between Brown University and Microsoft Research. So there are many examples of failures in distributed systems due to insufficient resource management. We've seen failures that cascade from one supposedly isolated availability zone up to a shared control plane, overloading resources in the shared control plane, like a shared queue, and ultimately spreading this outage to other availability zones. We've seen misconfigured background tasks that are allowed to aggressively consume resources until they eventually bring down the entire system. We've seen outages when unmanaged resources like database locks unexpectedly become bottlenecks after system code is updated or workloads change. We've seen bottlenecks occur due to some resources being left out of the scheduling and management components, such as disk and HDFS throughput lacking in yarn. In these examples, a lack of comprehensive resource management can cause problems up to and including entire system outages. So in this work, our goal is to actively control multi-tenant systems to provide resource management guarantees and hopefully prevent these sorts of outages. This is a challenging problem, though, for several reasons. First, requests from users traverse the same shared processes, and there are many resources that can become bottlenecks, system resources like disk, CPU, and network, as well as application-level resources like locks and thread pool queues. OS and hypervisor mechanisms don't have visibility into which tenant is responsible for resources being consumed by a shared process, and neither are they involved in managing those application-level resources. On the other hand, requests traverse multiple processes, machines, and services during execution. So to provide guarantees at the level of a request, we must coordinate all resources along the execution path, as any one of those could become a bottleneck. When we think of shared systems today, many of us think of containers and virtual machines as providing a sufficient level of resource isolation. But in many cases, underlying these, we do have a wide variety of shared systems providing common services like storage, databases, queuing, and coordination. And these systems are vulnerable if their resources aren't carefully managed. So given this resource management mismatch for shared systems, we introduce Retro. Retro is a comprehensive framework that performs active resource management in multi-tenant distributed systems. Retro monitors resources in the distributed system in near real time, and it actively throttles the tenants and activities in the system to achieve some high-level resource management goal. Those goals are specified as high-level centralized resource management policies that encapsulate the logic of resource management independent of the underlying resources or system implementation specifics. Retro provides 3 novel abstractions to make it easy for us to write these resource management policies. And in the paper, we present 3 resource management policies to achieve different goals, for example, to provide a guaranteed average latency to a user. To make things more concrete, I'm going to demonstrate an example in the context of the Hadoop file system. For those unfamiliar with HDFS, it comprises a central name node, which manages the file system metadata, and multiple data node processes, which store the actual file data. A file in HDFS is split into several blocks, and those blocks are dispersed among the data nodes of HDFS. A metadata operation, such as a rename, will typically only contact the name node, or a client reading or writing files will first contact the name node to acquire the locations of the files blocks, and then contact the relevant data nodes. Along the way, there are several resources that are consumed, such as a shared RPC thread pool queue and a read-write lock on the name node, and of course system resources like disk on the data node. In this experiment, this tenant is running a continuous loop of random 8 kilobyte reads, and over time, the latency of this tenant's requests look like this. We see that there are 3 periods of increased latency corresponding to the introduction of 3 other tenants. The workloads from the other tenants cause congestion on shared resources in HDFS and increase the tenant's overall end-to-end latency. The first workload is another tenant making repeated 4 megabyte reads from HDFS. This causes congestion on disks on the HDFS data node and increases the average latency of disk operations, thereby causing an overall increase in end-to-end latency. The second workload is a tenant repeatedly listing file system directories. This causes congestion on the name node's incoming RPC queue, increasing queuing time for everyone and impacting the end-to-end latency of our tenant. And finally, the third workflow is a tenant repeatedly renaming files. This causes congestion on the name node's read-write lock. Previous workloads only needed read locks. This workload needs write locks. Again, this increases the end-to-end latency of our orange tenant. And this experiment demonstrates several of the challenges faced by Retro. We see that different workloads can interfere with each other in different ways. Different resources can become different bottlenecks, including system-level resources and application-level resources. Bottlenecks can appear anywhere along the execution path, and they can change as the active workloads vary. And for concreteness, the Yarn resource manager, which is commonly present alongside HDFS, doesn't manage these resources and can't prevent interference like this. The picture becomes worse when we consider the type of environment where we'll typically run HDFS. Here we had tenants going to the HDFS data nodes, but we might also co-locate applications such as HBase, a distributed database. Requests to HBase also consume system resources, either directly or via HDFS. We might also co-locate MapReduce, a data processing and analytics framework. MapReduce jobs can consume system resources directly through HBase or through HDFS. Requests to these systems traverse multiple machines and multiple processes. So from these challenges, we derive some goals for Retro. First, we need to coordinate the control of resources across these varying processes, machines, and services. We need to make sure that we can handle system-level resources and application-level resources. We need to make sure that all tenants and tasks within our system are accounted for. And in order to deal with changing workloads and bottlenecks, we have to operate in real time. And finally, we should try not to affect the users of our system if doing so won't help with our resource management goal. So that is, once we've achieved some resource management goals, such as sharing a resource, we want to make sure that we maximally utilize the remaining capacity. I'll now talk about Retro's architecture and the three abstractions that we introduce. So one of the first things that Retro needs to be able to do is to identify which tenant's request is currently being executed at any point in time by this shared process. And typically, we don't have this level of visibility in systems today. To broach this, Retro introduces the workflow abstraction. A workflow typically corresponds to the requests submitted to the system over time by one user, or say a background task over time like data balancing. And a workflow is the unit of resource measurement, attribution, and enforcement in Retro. A Retro workflow is orthogonal to threads, processes, and network flows, which are the unit of resource management in some other systems. And to identify workflows, Retro must propagate at the application level alongside the execution of every request and identifier using similar techniques to end-to-end tracing, like Xtrace. At any point in time, this therefore enables Retro to query for the currently executing workflow. So next, Retro needs to be able to cope with the diversity of resources consumed by workflows, and we introduce an abstraction for resources. We don't want to care about their low-level implementation details. In fact, to manage resource usage, we only really need to care about two things. First, we need to identify which resources are overloaded. And second, we need to identify who is responsible for overload. So our resource abstraction captured these with two metrics. First, to identify congestion on resources, we have the slowdown metric, which says how slow the resource is now compared to its uncontended baseline performance. All we need from slowdown is to identify overload, not necessarily to be precise. Second, in order to attribute congestion to workflows, we have the load metric. Load helps us divide resource consumption among the workflows to determine who is responsible for the congestion. To make this concrete, we'll look at a quick example. Consider a thread pool queue. The more overloaded a thread pool is, the longer requests will wait in the queue before executing. So an uncontended queue will have a wait time of 0, and then therefore we have a slowdown of 1. If we waited 100 milliseconds in the queue, then executed for 10 milliseconds, this would have a slowdown of 11. The load imposed by a workflow on a queue is simply the total time spent executing after being dequeued. To reiterate, what we need from these metrics is to identify overload, not necessarily to be precise, and also to apportion load. The third retro abstraction that we introduce is for enforcing resource management decisions. Control points are decoupled from resources. There are points during the execution of requests where retro can rate limit workflows. The underlying implementations that we can use vary, and in our prototype, we used token bucket rate limiters where it's okay to pause threads, and RPC workflow-based priority queues for queues. To give an example of how a control point is used, and to motivate the abstraction, suppose this tenant is being aggressive and ultimately overloads this resource. We can rate limit the tenant across all processes and application tiers to reduce the tenant's throughput and to relieve congestion. And this is what control points gives us the ability to do. So retro aggregates per workflow resource measurements locally within each process, and then once per second aggregates these measurements centrally on a central controller. This gives us a place with near real-time global abstracted view of the system, its resources, and all the workflows that are currently executing. Using retro's abstractions, we can now write resource management policies that run on the central controller, that run in a continuous control loop, reacting to the per workflow resource measurements and making decisions about which workflows to rate limit. Retro coordinates the enforcement of policy decisions using per workflow distributed token buckets that tie back into Retro's application level control points. Retro's controller can be viewed as a control plane for resource management. Retro's API provides this global abstracted view of resource consumption in the system, and we can write policies that encode resource management logic without being tangled up with the underlying implementation specifics of the resources, measurement, or enforcement. So what does a resource management policy actually look like? In the paper, we present 3 policies, and I encourage you to look for more details because they're very different policies. Here I'm going to present our latency SLO policy. This provides an average latency guarantee to one or more high-priority workflows, which is something along the lines of 200 milliseconds average latency per request. There are also several low-priority workflows, which are allowed to use the spare capacity of the system so long as the high-priority workflows are achieving their latency guarantee. The policy continually monitors the request latency of the high-priority workflows, and if they are starting to get worse than their guaranteed latency, the policy will attempt to identify which resources are bottlenecks, and then which low-priority workflows might be causing those bottlenecks, and then throttle those low-priority workflows as appropriate. So this is what the policy actually looks like. Words highlighted in blue correspond to Retro API calls that directly map to our abstractions. So I'm going to cover this up, but I will uncover it and step through the code. But first I'm going to describe at a high level what the policy is actually doing. So first, we need to select the high priority workflow W that has the worst SLO performance. That is, the workflow that's either furthest away from achieving its guaranteed latency, or if all the high-priority workflows are achieving their guaranteed latency, the high-priority workflow that is closest to violating that guarantee. Second, given this workflow W, for all the low-priority workflows, we will calculate a weight corresponding to their interference with the high-priority workflow. Interference is determined by whether the low-priority workflow is consuming the same resources as W and is weighted according to how congested those resources are. And then third, we throttle these low-priority workflows in proportion to the weight that we just calculated. This policy runs continuously in a loop on the controller, and it just makes small incremental changes each iteration. Looking now at the policy itself, here to determine W, the worst performance is just the high-priority workflow with the highest ratio of current latency to promised latency. Next, to calculate interference, we first calculate the importance of each resource by looking at the slowdown of that resource, i.e. how congested it is, and combined with the amount of time that the high-priority workflow spends on that resource. This represents the amount of latency that can be reclaimed by decongesting that resource. Next, we calculate low-priority workflow weights by combining the resource importance with the load that each of the low-priority workflows has on the resource. This gives us a weight for each low-priority workflow. Finally, after normalizing the weights, we adjust the control point rates of the low-priority workflows, If the high priority workflow is missing its target latency, workflows are throttled according to the weight we calculated. Or if they're all achieving their target latencies, we relax the low priority workflows to allow them to utilize spare capacity. Finally, we send out new control point rates to the system. Since this policy works incrementally in a control loop, we have parameters alpha and beta, which control the size of steps taken in each iteration. In the paper, we also presented a bottleneck fairness policy, which simply selects the most overloaded resource and throttles tenants to try to fairly share that bottlenecked resource. And we presented a dominant resource fairness policy. DRF is a popular multi-resource fairness algorithm that generalizes maximum fairness for multiple resources. Retro's DRF policy is an iterative policy that uses slowdown to estimate capacity and estimates workflow demands by their observed resource consumption. In all cases, these policies are concise. They're agnostic to the specific underlying resource types, and they're independent to the underlying system that they're operating on. For example, we originally wrote these policies for HDFS, and then later we decided to incorporate more systems. And we could run these policies on these other systems without actually having to change the policy at all. So let's move on now to evaluation. To give a few implementation details, we implemented Retro in Java. It consists of an instrumentation library for adding Retro to your distributed systems, as well as a central controller implementation. The instrumentation library contains instrumented resource class wrappers, control point implementations, and a library for workflow ID propagation. To measure resource consumption, Retro intercepts API calls and aggregates counters in memory. These are reported to the Retro controller periodically, so overheads remain low. The currently executing workflow ID is stored in a thread local variable and has to be explicitly passed between threads, across RPCs, or through thread pools and queues as a workflow executes. However, much of Retro's instrumentation is actually done automatically using AspectJ, which modifies Java bytecode dynamically at build or load time. So as a result, adding Retro actually only required between 50 and 200 lines of code per system that we instrumented. In addition, since Retro only aggregates counters in memory, the maximum overhead that Retro has on throughput and end-to-end latency for a variety of HDFS benchmarks was between 1% and 2%. We ran experiments on 5 open source systems, and we ran a variety of workflows, including benchmark suites, simple workload generators, and we instrumented several background tasks in these systems. Many workflows, such as, say, MapReduce jobs, traverse several systems during their execution and require this coordinated management. We managed CPU, disk, and network at the system level, and application-level locks and queues within HDFS and HBase. As mentioned, we implemented 3 different resource management policies. So in the paper, we present various experiments with results on clusters up to 200 nodes. In this talk, I'll demonstrate the results for the latency SLO policy with workflows specifically in HDFS and HBase. So in this experiment, we have 3 high-priority workflows. We have an HDFS client making continuous random 8 kilobyte reads. We have an HBase client reading rows at random from a large on-disk database table. And we have an HBase client reading rows from a database table cached in memory by HBase. We have 3 low-priority workflows. We have an HBase client scanning a large on-disk database table. We have an HDFS client continually making directories. And we have an HBase client scanning a database table that HBase has cached in memory. We show the latency of the high-priority workflows over time, with 3 periods where we temporarily make each low-priority workflow more aggressive. The y-axis of this figure is normalized to the high-priority workflow's SLO, such that a value above 1 means that they have higher latency than the guarantee, which is bad. So we can observe what happens to the slowdown of each resource in our system over time as these low-priority workflows are intermittently more aggressive. The HBase table scan scans a lot of data on disk, thereby increasing disk slowdown. CPU is overloaded by the HBase cache table scan because the table is already in memory. The HDFS file system metadata lock is heavily loaded for the duration of the experiment, but increases when the client is more aggressive. That client also increases the slowdown on HDFS's incoming RPC queue. And finally, the HBase incoming RPC queue is overloaded by the HBase cache table scan. Now we repeat this experiment with the SLO policy enabled. And this graph shows the new latencies for the high priority workflows when the policy is running. And we see that even though the low priority workflows still affect the high priority latencies, the policy successfully prevents their latencies from going above their guaranteed latency. To see how the policy is rate limiting the low priority tenants, we can observe the rates that we're allocating them at the control points. This figure shows us the ratio of allowed control point throughput versus actual for one of our low priority workflows. When the line hits 1, this means the workflow is being actively throttled. And below 1 means that the policy is giving some amount of headroom to the low priority workflow to utilize the spare capacity. So here we see that the table scan is correctly identified by the policy and throttled when it's the aggressor. And here the policy identifies disk as being the primarily bottlenecked resource. The HDFS MapReduce client is also correctly identified and throttled when it's the aggressor. And in this case, the most bottlenecked resource is the HDFS file system metadata lock. We did see that that lock was heavily loaded for the duration of the experiment, and that's reflected in the fact that this client is not given as much room to grow as the other clients. And finally, the cached table scan is also correctly identified and throttled by the policy, and here the most overloaded resource was the HBase incoming RPC queue. So to conclude, we saw many challenges in resource management for shared distributed systems. And we saw examples of outages in the real world due to a lack of comprehensive resource management. Retro is a framework for centralized resource management with a goal of being comprehensive across the resources, processes, and workflows of the system. We provided 3 key abstractions that enable us to write and evaluate several concise general purpose policies. So with that, I will invite questions from the audience.
Hi, I'm Rodrigo from Princeton. So you had the running example of using HDFS, and I was wondering how common is it that multiple tenants share HDFS clusters?
So our setup was, we decided to focus on HDFS and HBase co-located because actually this work originally sort of spun out of our work looking at Windows Azure storage, which in our experience looking at sort of internal outage reports and that sort of thing do experience some of the resource contention patterns that I outlined in the talk. Furthermore, while this does sort of look storage specific, we did look at a variety of different workloads, computationally intensive MapReduce jobs, that sort of thing. And all throughout, we did design the system to try to be as system agnostic as possible.
Thank you.
Yeah.
Malte Schwarzkopf from Cambridge. So it's nice work. I also have a question about the HDFS use, because HDFS is maybe not the most high-performance system that was ever developed by anyone in the world. Yeah. So it is a bit of a kickback where it's very easy to find things that don't work very well. Specifically, like MICDA in a tight loop in HDFS is not a common workload and certainly not optimized for that. Which is not to say that people don't do that in practice, but I was wondering, because you said you also instrumented Zookeeper, if you found any interesting results from looking at Zookeeper.
Right. So Zookeeper is, for those unfamiliar with it, it's a coordination service, and it doesn't provide really any multi-tenancy whatsoever. Multiple people can use it, but it doesn't try to provide any isolation. So requests from any users in Zookeeper will be blocked behind requests from any other user. So certainly if you have a client who wants low latency requests and another client who happens to just be transferring large things, then it's very easy to increase the latency of those clients. We have a figure that I neither have on a backup slide nor in the paper, but that I can show you afterwards, where we did run an experiment in Zookeeper. In that case, the bottleneck would typically be the shared log, which batches requests and I think pushes them to disk or something like that. We did some special handling for that, and I'd love to talk to you about it afterwards.
Quick, sorry.
Yeah.
I think we're running out of time.
Okay. All right. Edward.
I'm Edward from Cornell. I think this is a cool idea, and you gave some good intuition for how you could automatically inject the instrumentation for measuring things on unmodified or basically unmodified code, but how do you figure out where the... Can you give some intuition for how you figure out and inject the code for those control points, those different hammer points where you can throttle clients, given that you don't really know in advance what they're going to be?
Yeah, that's a very good point. So actually, the short answer to that is control points were one of the few parts of Retro that we did apply some sort of intuition about placing, because you don't want to place them at such a low point in the system code where they could be conflicting with, say, the operating system's disk scheduler. So they have to be high enough to allow the lower level schedulers to do their thing, but they also can't be so high level, such as like just general admission control to the system, which means that your system is so slow to converge that you can't really do anything. However, that being said, in our case, we only implemented I think there were 2 lines of code modification to add our control points. One was just an explicit line of code that we placed in HDFS's data transfer threads, because HDFS has a sort of application level packet that it sends. And then the second was the general purpose RPC and RPC queue mechanism in HDFS and HBase that all the systems share. We can just place a priority queue in front of that. And those alone were sufficient. But this is a great point.
Thank you.
Thanks.
Let's thank the speaker again.